The method of integration by substitution can be quite useful when other methods aren't working. And in order to do it, we need to rely on just the chain rule, the fact that when we integrate a function in terms of x with respect to x, we can replace the dx by a dx du. So that's going to enable us to integrate with respect to u, and we just need to remember to multiply by this dx by du term. It sounds a bit strange at first, but when you do a few examples, I'm sure you'll understand what I'm talking about. Okay, so we'll start with this one. We've got to integrate x over the root of x minus 2 dx, and we're told to use the substitution u is equal to x minus 2. In practice, you are almost always told what to use as the substitution. When I say in practice, I mean in exams, you are almost always given the substitution to use. But it's always, after you've done a few, it will be quite obvious anyway. So we're going to replace all the parts in the integral over here by u's. So obviously the bottom part of the integral is just u, because we've been told to use the square root of x minus 2 as u. So then we've got to replace the top. So if we say that u squared is going to be x minus 2, so x would be u squared plus 2. So we can replace the top of the integral by u squared plus 2. Okay, now we've also got to replace the dx by a dx du. So easiest way here is to integrate this term that we've got here. So dx du is 2u. Okay, so we need to then put our dx du is 2u term in, and then du. So this bit was here, and then we just can integrate with respect to u. Okay, so we can cancel out one of the u's here, and we're just left with the integral of 2u squared plus 4. Okay, just multiplying out the two terms we've got there, and that's with respect to u. So we've got 2/3 u cubed plus 4u. Now, we weren't asked to integrate with respect to u. We were asked to use the substitution, but we need to take it back to x. So we could just put at this point 2/3 of x minus 2 to the 3 over 2, because it was the square root of that, and then cubed, plus 4 lots of x minus 2 plus c. So that could be our answer. However, I think it's nicer if we factorise the answer at this stage. So if we take out from here 2 lots of u, and then we can put that as u squared over 3 plus 2. Okay, and then replace our u. So we've got 2 lots of the square root of x minus 2 multiplied by u squared is x minus 2 over 3. Whoops, didn't mean to put that. Okay, u squared over 2 plus 2. Okay, let's just make that a little bit smaller so I've got a bit more space to finish off. Okay, so that is 2/3 of the square root of x minus 2, taking out the third, so I've just got x minus 2 here, and then plus 6, so that's then multiplied by x plus 4. Okay, plus c, of course. Okay, so this answer is okay. This answer is, I think, a little bit better. Okay, let's try another example. Okay, so this one tells us to use a suitable substitution. So it's not difficult. If you look at the integral to see that this bit here is the awkward bit of the integral, so we'll make that equal to our u. So we say u is 3x squared plus 6. So when we come to replace everything in the integral by u, we're going to have a u cubed term there. Now I'm going to leave the x term for the moment, you'll see why in a second. So I'm just going to differentiate here, so du by dx is going to be 6x. So by the special case of the chain rule, dx by du is going to be 1 over 6x. So when I replace dx by, or when I add in the dx by du term, I'm going to write that as 1 over 6x, and then I can integrate with respect to u. So you can probably see why I did that. The x will cancel with the x here, and then I've just got an integral in terms of u. So I've got the integral of 1/6, which I can pull out, of u cubed with respect to u. Nice and simple. So that gives me u to the 4 divided by 4, and the 4 is multiplied by the 6, so u to the 4 over 24 plus c. Okay, so I need to substitute back my u, so 1/24 of 3x squared plus 6 to the power of 4 plus c is the answer. Okay, so this time we've got a definite integral. Now you can do what we've just done with the others, and you can go back to x at the end, but there is a quicker way of doing it, which is if you replace also your limits. So if we say, okay, we're using u equals x minus 1, so these limits up here are for x. So if we know that x is equal to 1, then u is going to be 1 minus 1 or 0. And our other limit is x equals 0, so our u limit that's associated with that will be minus 1. So we can change our limits as well to be limits for u, so we'll put them as 0 and minus 1. Now sometimes when you do this you get a lower, this one hasn't, but sometimes you get a lower limit at the top, but you still put them in the order that they appear in the integral. So if we'd got a lower value for x is 1, then that would still go at the top of the integral. Okay, so we know that this part is u to the 4. Okay, so we've also got to replace x, so x, So we've also got to replace x, and if u is x plus 1, x is going to be, sorry, u is x minus 1, x will be u plus 1. So we're going to put in a u plus 1 here. So x is replaced by that, that's replaced by that. We've got to have a dx by du term, but this time dx by du is just 1. So multiply that by 1, and then we can integrate with respect to u. So that simplifies to u to the 5 plus u to the 4 du between 0 and minus 1. So integrating that, sorry I haven't put my equal signs in, we've got u to the 6 over 6 plus u to the 5 over 5. And we don't need to replace our x because we've already changed our limits, so these now correspond to u. Okay, so putting 0 into both of those terms will just give us 0. And then we've got minus 1 to the power of 6 will give us 1/6. And then minus 1 to the power of 5 will give us minus 1. So plus there, minus 1 over 5. Okay, so that's minus out from outside the bracket. And that's 5/30 minus 6/30, so it's minus 1/30. Doesn't seem to want to write there, let's just move it up a little bit. So we've got minus 1/30, minus 1/30, or just a 30th. Dear me, I'm having trouble with my pen. Okay, 1/30 is our answer there. Okay. Now, you often get integrals, this one's in terms of, it's both trig in the question and trig in the substitution. Sometimes you get one that you wouldn't think for a minute to use trig for, but it's suggested that you use a trig substitution, so you just go with it. It's given to you for a reason. But let's just have a look at this one. So we've got u equals tan x, and if we differentiate that first of all, so du by dx will give us sec squared x. Now that's obviously related to what we're integrating. So dx by du, by the special case of the chain rule, will be 1 over sec squared x. Okay, so if we just start off by putting that into the integral, so we'll leave our sec to the 4x, we'll put in our dx by du, which is 1 over sec squared x, and then du. Okay, now it doesn't make sense to integrate that with respect to u because it's all in terms of x still, but let's see what happens next. So obviously the sec squared x will cancel with sec squared x here, so we've just got the integral of sec squared x du. Still doesn't make any sense, but what we know is that sec squared x is equal to tan squared x plus 1, and that is actually u squared plus 1. So what we're integrating here is u squared plus 1 with respect to u. Okay, so that's going to be u cubed over 3 plus u plus a c. So we can just write that as tan cubed x over 3 plus tan x plus c. We could have factorised here and taken out a term of u over 3, and then we'd have u squared plus 3, and substituted there. Doesn't make much difference, it's not particularly beautiful that way either. Okay, so now as I say, you're almost always in the exam you're given the substitution, and what you have to remember is to replace every part of your integral by u. So you need to do that dx by du term and substitute that in. You need to remember, if you've got limits, to change them to u as well. And if you haven't got limits, if it's not a definite integral, you've got to remember to put your x back at the end. Okay, those are the main points, I think.